subdiscipline of chemical ecology, which has taken an exceptionally reductionist, high-technology approach to studying chemically mediated processes, such as plant defenses against herbivores. And as a chemical ecologist and evolutionary biologist, this hurts. And my argument to Dr. Brown would be that I think that virtually all of life interacts with third world chemistry. Most of life, actually, I think, interacts pretty exclusively through chemistry, and we're sort of the oddballs. I mean, later today, some of you are going to go out and have drinks. You're interacting with your world chemically that way. Your gut microbes are using quorum sensing to digest said drinks. So chemistry is all around us, and I think it's just underappreciated. And so, like most phenotypes, many of these chemically mediated phenotypes, or chemotypes, both function and evolve as complex multivariate traits. And by complex multivariate traits, I mean that they vary both qualitatively, in terms of the different molecules involved, and quantitatively, in terms of the relative abundances or total abundances of each of those compounds. And so, for this talk, I'm going to use examples from my research on the chemical defenses in fireflies. And so, most of you are probably familiar with fireflies, bioluminescent beetles that use light signaling to attract mates. But many of you are probably not aware that fireflies are chemically defended. And they are chemically defended with a complex blend of cardiac steroids called bufadinolides, or sometimes lucifucogens, that really have a lot of very complex variation. And so, just as an example, this is a mass spectral chromatogram here of a subset of 90 individuals from my collection. And all of these peaks represent isomers of just one sort of class of bufadinolides, corresponding to a molecular weight of 364 Daltons, sort of like bufalin here. And so this is just a very small subset of the extant variation that I'm dealing with. And so for this talk, I'm going to make a sort of a gross generalization of fireflies and put them into categories. It's a lifestyle category, say. And so these three categories, we start with the bioluminescent fireflies. These are the ones we all know and love. They come out at night, they flash, they attract mates with that light signaling. And they're sort of the gestalt view that we think of. Well, so there's another group of fireflies that are diurnal. So these fireflies don't actually have light organs, or have lost them as adults, and instead they use pheromones to signal their mates. These guys here in yellow. And then my favorite sort of subgroup, lifestyle strategy, are fireflies in the genus Fordyce. These are a subset of bioluminescent fireflies that don't make these toxins on their own. Instead, they mimic the flashes of other firefly species, lure in hopeful males who think they're going to get lucky, then pounce on them, eat them, steal their toxins, and sequester them for both themselves and their offspring. And so, how might we try to analyze this complexity? Well, the classic way that we might do this is to completely ignore the qualitative aspect of the variation, lump everything together, and talk about total amounts. So, what happens if we do this? So, here we have lifestyle strategy on the x-axis, and we have the total amount on the y-axis, represented as the sum of the square root of each peak area. And if we run a mixed model, we can say, woohoo! There is a difference. We have a significant p-value. Science has been made. And specifically, you can see that the bioluminescent fireflies have not quite, but almost an order of magnitude more bufadinolides in terms of total amount. This makes sense, right? They're flying around at night, their butts are lighting up, they're pretty apparent to predators. So I can imagine that they might need a little bit more oomph to defend themselves. Unfortunately, total amount completely ignores the qualitative variation, and so we're missing part of the story here. So the next thing we might do is acknowledge the multivariate nature of the data and do something like an ordination, right? Something like an RDA or a PCA. And so what happens? These things are really nice because they can reduce sort of this high dimensional complexity down to a sort of more manageable few dimensions that we can think about. And so if we do this with my fireflies, we basically get some nice clustering, 3, maybe 4 groups. We get most of the bioluminescent Fordyce sort of clustering up top here. And then we get a group, another group, the Fordyce pyralis species, off to the side. And I'd like to talk more about this because I think it's really interesting, but I'm going to sort of ignore this for this talk. Then we get the pheromonal signalers down at the bottom here, and then, and I think this is really cool, right in the middle, we get the Fordyce, the sequesters. So this to me makes sense because these guys, that they'd be intermediate, because they're going out at night, they're grabbing whoever they can, so it makes sense that they sort of be right in the middle, sharing a little bit of everything. So while ordinations are really useful for visualizing these clustering patterns, it can be a bit hard to interpret, as anybody who's ever tried to think about eigenvalues and eigenvectors, interpreting loadings, etc. The only other thing about ordinations is that they don't deal with intra-individual variation, within individual variation. They start with pairwise distances as sort of a default, and so you're sort of losing that level. So what I wanted to do was sort of take a scorched earth policy and start from the ground up, and come up with a new way to sort of think about this stuff. And then I realized that there's also already kind of a framework out there that community ecologists have been dealing with for years, and that is to sort of think about this complexity in terms of a community and use well-known diversity indices, such as richness, Shannon entropy, the Jenny-Simpson index, to quantify this. And so the work of Hill and then Lou Jost and Chow has shown that all of these different diversity indices are mathematical transformations of each other. And if you do these mathematical transformations, they all are all put into units of effective number. And by effective number, I mean the equivalent number of, say, compounds in an idealized chemotype if all of those compounds have equal abundances. And so these effective numbers, these different indices, basically they differ in terms of their order and in terms of how they deal with disparity in abundance. And so when the order Q is 0, which corresponds to richness, we're completely ignoring the quantitative aspect of the variation and just dealing with presence-absence. When Q equals 1, which is equivalent to the exponential of Shannon entropy, in this case, all the compounds are weighted equally by their relative abundances. As you move up in order from Q equals 2 and beyond, compounds or components that are more abundant become increasingly influential, and compounds that are more rare or less abundant are increasingly down-weighted or dropped out. This is really nice because then we can use a diversity profile plot to look at both the qualitative and quantitative aspects of this variation. So here we have the order on the x-axis, and we have diversity as the effective number on the y-axis. If all components in the phenotype are completely even, we'd expect a straight line just like this. If there's some mild disparity, some compounds or some components are a little bit more abundant than others, we might expect something like this, where we start out high and then sort of taper off a little bit. And then, as is often the case, if there's large disparity with a few compounds that are really abundant and a lot of rare compounds, we'd expect something like this with a really strong negative slope. And just as with communities, we can partition this diversity into within group, among group, and pooled total components. And so in this cartoon here, let's imagine that this is the chemotypic space of a population. In this population, we have 3 individuals, individual 1, 2, and 3. Let's say that individual 1 has 1 compound, individual 2 has 2 compounds, and individual 3 has 3 compounds. We're going to ignore abundance right now. So we can then we can partition this into the total diversity, gamma, which is the total effective number of compounds overall in the population. So in this case, it would be 6. And sometimes gamma is interesting. Sometimes we are interested in the total amount. But just like in ANOVA, usually we're more interested in the within versus among group components. Alpha diversity then becomes the within group component, and it's the mean within group chemical diversity, mean within group effective number of compounds. In our case, we have 6 compounds overall, 3 individuals. So each individual has, on average, an effective number of 2 compounds. Usually, we're also more interested in the among group component, which is beta diversity. And beta diversity, in this case, is the effective number of completely distinct chemotypes, completely unique chemical cocktails or chemical mixtures that we might find in the population. And we can partition this out multiplicatively or additively. Then, we can use a hierarchical framework to partition this diversity at multiple levels to address chemical complexity at different scales. So for this talk, because of time, I'm just going to focus there. They're going to just by chance differ a lot among individuals, a lot more. But as you can see, they really differ mostly in the most rare compounds. Because as those rare compounds drop out, you get convergence and the differences go away between these through signaling modalities. And so, in conclusion, I really like this method, using diversity partitioning to describe this chemical complexity, because I think it succinctly addresses both qualitative and quantitative aspects of this variation, in at least a complementary way that some of these other methods don't. And I would add that this partitioning really simplifies this complexity and simplifies it while illuminating sort of these interesting qualitative and quantitative aspects, rather than doing what some of these other methods do, like ordinations, which often obscure the variation, obscure the complexity, and sort of black box it. And so, just in closing, I want to expand this out a minute. So I've pitched this in terms of chemical complexity, chemical ecology, and evolution, but it need not be chemical in nature. In this manuscript that we've just submitted, we analyzed soil functional traits, for instance. And I think that it could be really powerful for particular questions about things like behavioral syndromes or gene transcripts. If you're working on plasticity, it might be really nice to think about the beta diversity or disparity of different treatments in terms of sort of the transcripts and the gene expression levels. And so, I'd like to add that we are working on a R package for this that should be out pretty soon. And so I'd like to talk to you more about this and answer any questions you might have. Thank you.
So for the sequesterers, are those their sort of natal chemical compounds, or is that their chemical set of chemotypes after they've been ingesting stuff?
That's after they've been ingesting stuff. As far as we know, they don't actually produce these things de novo. They do produce a betaine, which is sort of a different class of compound themselves. But as far as the bufadinolides, as far as we know, it's all by predation.
Were you saying about some of those chemicals being like the most highly upregulated ones are the ones that are most common across taxa? Do you think that could be due to like maybe conversion evolution, because they're, aside from getting predated or depredated by each other, they're all getting eaten by other taxa? Or could it be a result of like dietary influences, like they can only build the chemicals that they can get based on what they're eating on?
Likely it's probably somewhere in between. I think, and I really didn't talk about this very much, but and at least with my preliminary data set, most of the variation in the chemistry is driven by species identity. And so I think there's probably some phylogenetic constraints on it, but we really don't know too much about that yet.